Hello, in this video I explained how to perform principal components analysis of your molecular dynamics trajectory using GROMACS tools. The purpose of principal components analysis is to capture the essential dynamics of your selected group of atoms. The process of doing this is more involved as compared to simple metrics like RMSD. You initially build and diagonalize the covariance matrix for atoms in your selected index group. For this you use the GMX covar tool. Among possible output files you're interested in ones containing eigenvectors corresponding to your principal components and eigenvalues. Further you analyze your trajectory file with eigenvectors and file with eigenvalues using GMX anaeig tool. You can also use the anaeig tool to analyze the data of normal modes analysis, which is the alternative to principal components analysis. However, normal modes analysis is not covered in this video. The anaeig tool provides you with different possible representations of your principal components as well as some secondary data related to them. For instance, you can obtain one-dimensional, two-dimensional, three-dimensional projections of your principal components for further analysis. You usually are only interested in the first three principal components as they capture most of the conformational motion of your index group. You further want to check if your principal components represent actual conformational motion but not some random diffusion, and you use GMX analyze tool for that. Particularly you use it to determine the cosine content of your first principal component. As a rule of thumb, you want your cosine content to be as close to zero as possible. In this video I will analyze the index group of the backbone of one of my protein subunits, which is fairly large. As I deal with globular atoms in this case, I expect the high values of cosine content as there is minimal actual conformational motion after protein folding, except for the disordered regions, for which I usually obtain low values of cosine content. have finished our calculations, let's check out the output files. Your main output is the XVG file with the projections of your trajectory onto the principal components. This allows you to plot on the graph motion along your principal components. Significant fluctuations of the graph curves indicate conformational transitions. Using XVG file with two-dimensional projection, you can visualize conformational motion along two principal components simultaneously. In this case, clusters of connected dots represent stable states, and the lines between them are the transitions between such states. As a secondary output, you can also obtain file with root mean square fluctuations of atoms in your index group about each principal component. Larger MSF values indicate higher contribution of atom into the conformational motion about particular component. As expected, we have obtained large Gaussian content in the first principal component. In many cases, the high values of Gaussian content indicate that the system has not converged yet and more sampling is required. However, in this case, the reason of high Gaussian content is very small variance of backbone atoms, which barely move. With the XVG file of eigenvector components, you can visualize for each atom in which direction about x, y, and z axis the motion occurs, and to which extent. So you basically can see which regions of your structure contribute the most to the conformational motion of particular principal component. By analyzing eigenvalues, you can determine how much particular principal component captures the collective motion of your selected index group of atoms. Now that we have plotted our data, let's check out the actual content of each file. files can be visualized with molecular visualization tools like Páll or ChimeraX. That way you can visualize the projection of your trajectory onto your selected agent vectors of principal components in three-dimensional space. You can also obtain the average structure of your selected index groups from your trajectory to overlay it with some extreme points of each principal component to see exactly which atom and in which direction spread in three-dimensional space. However, in this video I do not cover this part of PCA analysis, but I encourage you to check the manual and the description of the anaeig tool to see all possible types of output and how you can use them in your research. Thank you for your time and let me know if you had any troubles.